Tonight, we are going to explore the true scale of the Milky Way galaxy, not as a single number to be stated and moved past, but as something to sit with slowly, turning it over from many directions until the full shape of it becomes clear. The Milky Way galaxy is the structure we live inside, and understanding its true dimensions means understanding something about where we are in the universe and what it means to exist at this particular location within it. We will move through this gradually. We will look at how astronomers measure something they cannot step outside of, what the different regions of the galaxy actually are, how large each of those regions turns out to be, and how the whole thing compares to the broader structures that surround it. By the end of this evening, the Milky Way will feel less like an abstract fact and more like a place with genuine dimensions and character. You are listening to Sleepy Time Universe, calm science for curious minds seeking rest. Get comfortable and let your breathing slow. There is no rush tonight. We have the whole evening ahead of us. We will begin not with a number, but with a problem. The problem of measuring something from the inside. Chapter 1. The problem of measuring from within. There is a particular difficulty that comes with studying the Milky Way that does not apply in the same way to studying other galaxies. When astronomers turn their telescopes toward a distant galaxy, they are looking at it from the outside. They can see its shape. They can trace its spiral arms. They can measure how far across it appears in the sky and, knowing the distance to it, calculate its actual physical size with reasonable confidence. The geometry is straightforward because the observer and the object are entirely separate. With the Milky Way, this is not possible. Our solar system sits embedded within the disk of the galaxy, roughly 26,000 light-years from the Galactic Center. Everything we observe from this single fixed point within the structure itself. It is something like trying to understand the layout of a vast forest while standing among the trees. You can look in every direction, you can walk and measure. You can note what grows nearby and what appears faint and distant, but you cannot rise above it to see the whole shape at once. This creates genuine and lasting challenges for measurement. For most of human history, astronomers did not even know they were inside a galaxy. The stars visible to the naked eye, the band of light crossing the night sky, the occasional smudge of a distant nebula. All of these were observed and catalogued without any clear understanding of the larger structure they belonged to. The concept of the Milky Way as a discrete island of billions of stars rotating slowly through space is a relatively recent addition to human knowledge. The first serious attempt to map the structure we inhabit came in the 18th century. William Herschel, working through the 1780s and 1790s, developed a method he called star gauging. He counted the number of stars visible in many different directions across the sky, reasoning that directions with more stars indicated greater depth in that direction, that the galaxy extended further that way than in directions with fewer stars. His counts produced a map of sorts, an irregular flattened shape with the sun positioned near the center. This conclusion turned out to be incorrect, but the error was understandable given the tools and knowledge available to Herschel at the time. The fundamental problem was dust. The disk of the Milky Way contains enormous quantities of interstellar dust, fine particles distributed throughout the plane of the galaxy that absorb and scatter visible light. Stars lying far away in the plane of the galaxy are often invisible not because they are intrinsically faint, but because their light has been absorbed by dust clouds lying between them and us. Herschel's star counts were systematically limited by this dust, creating the false impression that stars thinned out equally in all directions, and that we sat near the middle of the distribution, This misunderstanding persisted for well over a century. It took a different kind of object and a different kind of reasoning to finally establish where we actually sit within the galaxy. Harlow Shapley, an American astronomer working in the years around 1915 to 1920, turned his attention to globular clusters. These are dense, roughly spherical collections of anywhere from tens of thousands to several million old stars, bound together by gravity into tight balls that orbit the galactic center in a broad halo surrounding the disk. Unlike the stars of the disk itself, globular clusters are bright enough to be seen at great distances, and Shapley had a method for estimating how far away they were based on the brightness of certain variable stars within them. What Shapley noticed was that globular clusters were not distributed evenly around the sky. They were concentrated heavily in one direction, toward the constellation we call Sagittarius. He reasoned that if these clusters orbited the center of the galaxy, and if they appeared concentrated in one part of the sky, then the galactic center must lie in that direction, and our sun must be far from it, offset to one side. His estimate placed the center at a distance of around 50,000 light-years, which turned out to be roughly twice the actual distance, but the essential insight was correct. We are not at the center of the Milky Way. We are somewhere in the outer regions of the disk, looking inward toward a center that lies far away in the direction of Sagittarius. This was a significant revision to humanity's understanding of its place in the cosmos. The Sun had already been displaced from the center of the solar system by Copernicus centuries earlier. Now it was being displaced from the center of the galaxy as well. Each step outward in our understanding of cosmic structure has tended to reveal that we occupy a less central, less special position than previously assumed. The galactic decentering of the Sun was another step in that long process of adjustment. The decades following Shapley's work brought new tools that allowed astronomers to see past the dust that had limited earlier observations. Radio astronomy, which developed seriously in the 1930s and expanded rapidly after the Second World War, opened an entirely new window on the galaxy. Radio waves at certain wavelengths pass through interstellar dust almost without interruption, allowing astronomers to detect sources on the far side of the galaxy that would be completely invisible in optical light. A particularly important discovery came in 1944, when Dutch astronomer Hendrik van der Hulst predicted that neutral hydrogen gas, the most abundant form of matter in the galaxy, should emit radio waves at a wavelength of 21 centimeters. This prediction was confirmed observationally in 1951, and the implications were significant. Since hydrogen is distributed throughout the disk of the galaxy, mapping the 21-centimeter emission across the whole sky effectively mapped the large-scale structure of the Milky Way for the first time. The resulting picture showed a disk with spiral structure, arms of higher density winding outward from a central region, broadly similar to the spiral galaxies astronomers had been observing in the distant universe for decades. Later came infrared astronomy, which also penetrates dust more effectively than visible light, and space-based observatories that could operate above the absorbing effects of Earth's atmosphere. Each new capability added resolution and detail to the picture. The positions of millions of individual stars were measured with increasing precision. Distances were refined, and the large-scale architecture of the galaxy became progressively clearer. More recently, the Gaia space mission, operated by the European Space Agency and launched in 2013, has measured the positions and motions of nearly 2 billion stars with extraordinary accuracy. The data from Gaia has revealed fine details of galactic structure, identified stellar streams from ancient merger events, and refined estimates of the galaxy's dimensions and mass with a precision that was not previously achievable. And yet, even with all of this, the Milky Way is not fully mapped. Regions on the far side of the Galactic Center remain difficult to observe because so much dust and gas lies along those lines of sight. The outermost regions of the galaxy are sparsely populated and faint. Some of the most fundamental measurements, the exact distance to the galactic center, the precise diameter of the disk, the total mass of the system, carry uncertainties that continue to be refined with each new generation of instruments. This ongoing incompleteness is worth keeping in mind as we move through the rest of this exploration. The numbers we will encounter are well established in their broad outlines, but they are not fixed the way a textbook entry might suggest. They are living estimates, the current best understanding of a community of scientists working with imperfect tools on a genuinely difficult problem. The galaxy is still giving up its secrets, slowly and on its own terms. There is something appropriate about that. A structure as large as the Milky Way, containing hundreds of billions of stars spread across 100,000 light-years of space, should not yield easily to measurement. The difficulty is part of what makes the measurements meaningful when they finally arrive. Chapter 2. The Disk, its width and thickness. The most familiar image of the Milky Way is the band of pale light that stretches across the night sky on a clear, dark evening, far from city lights. It runs from horizon to horizon, diffuse and soft at the edges, slightly brighter toward certain regions, and it has no sharp boundary anywhere along its length. This band is what we see when we look along the plane of the galactic disk from our position embedded within it. We are looking sideways through the disk, and the combined light of billions of stars too distant to resolve individually blends together into that familiar glow. The disk itself is a flattened structure, much wider across than it is thick. If you could somehow view it from a great distance above or below, it would appear as a broad, thin plate, slightly thickened at the center, where the galactic bulge rises above and below the plane, and thinning gradually toward the outer edges. The proportions are somewhat like a very flat lens, or perhaps like a vinyl record with a slightly raised center, though neither analogy captures the full complexity of what is actually there. The diameter of the disk has been a subject of ongoing refinement. For several decades, the standard figure given in textbooks was approximately 100,000 light-years. This number remains a reasonable approximation, but more recent measurements have suggested the disk may extend somewhat further than this in certain directions. Studies using data from surveys of stars in the outer regions of the galaxy have found stellar populations at distances suggesting a disk diameter of perhaps 160,000 light-years, or possibly even larger in some directions. The outer disk does not end cleanly. It becomes progressively more sparse, fading out rather than stopping at a defined boundary, which makes the question of exactly where the disk ends somewhat dependent on how you define the edge. For the purposes of developing a clear mental picture, 100,000 light-years across is a useful working figure. It is the distance that light, traveling at just under 300,000 kilometers per second, would take 100,000 years to cross. Our entire solar system, from the Sun to the outermost reaches of the Oort cloud, spans perhaps 1 to 2 light-years. The galaxy is roughly 50,000 to 100,000 times wider than that. Placed side by side, you could fit an almost incomprehensible number of solar systems across the galactic disk. The thickness of the disk is considerably smaller than its width, but it is not uniform. Astronomers distinguish between two overlapping components that together make up what we call the disk. The first is called the thin disk. This is the region where most of the galaxy's star formation activity occurs, where the spiral arms are most prominent, and where relatively young, bright blue stars are found alongside older stars and large clouds of gas and dust. The thin disk extends roughly 1,000 light-years above and below the central plane of the galaxy. That is the region where our own Sun resides, sitting a modest distance above the exact mid-plane. The second component is called the thick disk. This is a broader, more diffuse population of stars that extends roughly 3,000 light-years above and below the plane. The stars of the thick disk tend to be older than those of the thin disk, contain fewer heavy elements, and move on somewhat more tilted orbits around the galactic center. The thick disk is thought to represent an earlier phase of the galaxy's history, a population of stars that formed when the Milky Way was younger and its structure less settled than it is today. Together, the thin and thick disk create a layered structure. If you could stand far enough away from the galaxy and look at it edge-on, you would see the thin disk as a bright, narrow band running along the center, embedded within the broader, fainter glow of the thick disk. The whole assembly would look remarkably flat compared to its width. The ratio of thickness to diameter is roughly comparable to a sheet of paper, or perhaps slightly thicker. Within the disk, matter is not distributed uniformly. Stars cluster into the spiral arms, which are regions of somewhat higher density winding outward from the central regions. Between the arms are interarm regions, where stars are less densely packed. Gas and dust are also concentrated in the spiral arms, which is why the arms are regions of ongoing star formation. The density of material there is high enough for gravity to pull gas clouds together into new stars. The disk is, in this sense, not a static structure, but an active one, with new stars forming in some regions while older stars continue their long orbits throughout. The disk also warps slightly. Astronomers have known for some time that the outer regions of the galactic disk are not perfectly flat. They curve upward in some directions and downward in others, in a pattern sometimes described as a warp or a twist. The cause of this warp is not entirely settled, but it is likely related to the gravitational influence of the galaxy's largest satellite galaxies, particularly the large and small Magellanic Clouds, which pull on the outer disk as they orbit. This warping is gentle by cosmic standards. The deviation from flatness is a small fraction of the disk's overall diameter, but it is a real feature of the galaxy structure, a reminder that the Milky Way is not isolated, but exists within a gravitational environment that shapes it continuously. The disk is also rotating. Every star within it, including our Sun, moves in a roughly circular orbit around the galactic center. The Sun completes one full orbit approximately every 225 to 250 million years, a period sometimes called a cosmic year or a galactic year. At the Sun's distance from the center, this orbital motion amounts to a speed of around 230 kilometers per second. That is fast by any everyday standard. It is roughly 800 times the speed of a commercial aircraft. And yet, at the scale of the galaxy, it produces an orbital period measured in hundreds of millions of years. Scale has a way of changing what speed means. The rotation of the disk is not uniform in the way that a solid object rotates. A spinning top or a wheel rotates such that all parts of it complete one revolution in the same amount of time. The galaxy does not work this way. Stars at different distances from the center orbit at different speeds, and the relationship between orbital speed and distance from the center tells astronomers something important about the distribution of mass within the galaxy. We will return to that relationship later, when we consider dark matter and what it reveals about the galaxy's true extent. For now, it is enough to hold in mind the image of a vast, slowly rotating disk, hundreds of thousands of light years across and a few thousand light years thick, with our sun sitting quietly within it, completing its long journey around the center at a pace that makes human timescales feel very small indeed. Chapter 3. The Spiral Arms. If you were able to view the Milky Way from a position far above its disk, looking down on the whole structure at once, the first thing you would likely notice is the spiral pattern. Bright curving lanes of stars and glowing gas winding outward from the central regions, separated by darker interarm spaces, the whole assembly slowly rotating like an enormous pinwheel suspended in darkness. This is the defining visual feature of a spiral galaxy, and the Milky Way possesses it, though the precise details of our own galaxy's spiral structure have taken a long time to establish and are still being refined. The challenge, once again, is that we are inside the structure we are trying to map. Seeing the spiral arms of a distant galaxy is straightforward. You simply observe it from outside and trace the bright regions. Mapping the spiral arms of our own galaxy requires working from within, inferring the large-scale pattern from the distribution of objects we can observe in many different directions across the sky. It is a more indirect process, and it has produced results that have been revised several times as measurement techniques have improved. The current understanding is that the Milky Way has 4 major spiral arms, each winding outward from the central bar region across tens of thousands of light years. These 4 arms are known by the names of the constellations in whose direction they are most prominent when viewed from Earth. The Perseus arm winds through the outer galaxy in the direction of the constellation Perseus. The Sagittarius arm curves through the inner galaxy towards Sagittarius. The Centaurus arm, also sometimes called the Norma arm, or the Scutum Centaurus arm, is one of the more prominent features of the inner galaxy, and the Cygnus arm, sometimes called the outer arm, represents one of the more distant features of the disk. Our solar system does not sit within any of these 4 major arms. Instead, it lies in a smaller, shorter feature sometimes called the Orion arm or the local arm, positioned between the Perseus arm and the Sagittarius arm. This local feature is a spur rather than a full spiral arm, a branch of denser material extending outward from one of the major arms rather than a continuous structure winding all the way around the galaxy. The Orion Nebula, one of the most well-known star-forming regions in the sky, lies within this local spur, as does much of the star-forming activity visible to us in the nearby galaxy. The spiral arms of the Milky Way are not simply regions where stars are more densely packed. They are regions where star formation is actively occurring, marked by bright young stars, glowing clouds of ionized gas called HII regions, and dense molecular clouds where new stars are in the process of condensing. The arms are bright because they contain a higher concentration of the most luminous objects, massive young stars that burn intensely and briefly before ending their lives in supernova explosions. These stars are so bright that they dominate the light of the arms, even though they are vastly outnumbered by older, dimmer stars. There is an interesting subtlety here worth dwelling on. The spiral arms are not permanent structures in the way that the spokes of a wheel are permanent. If they were rotating rigidly with the rest of the disk, they would wind tighter and tighter over billions of years until the spiral pattern was lost entirely. This winding problem, as astronomers call it, was recognized early in the study of spiral galaxies, and its resolution took some time to work out. The explanation that emerged is that the spiral arms are density waves, regions of slightly higher gravitational density that move through the disk at a different speed than the stars themselves. Stars and gas clouds pass through the arms as they orbit the galaxy, spending time in the denser region before moving on. When gas clouds enter the denser region of a spiral arm, the increased gravitational compression can trigger the collapse of the cloud into new stars. The bright young stars that result illuminate the arm from within, making it visible. By the time those stars have aged and faded, the gas from which they formed has moved on through the arm and out the other side. In this picture, the spiral arms are somewhat like a slow-moving traffic jam on a highway. Individual cars, stars and gas clouds flow through the jam and emerge on the other side. The jam itself, the region of higher density, moves at its own pace, maintaining its pattern even as the individual components within it are continuously changing. The stars we see lighting up a spiral arm today are not the same stars that lit it up 100 million years ago. The pattern persists even as the contents cycle through. This understanding helps explain why spiral arms are so prominently marked by young stars and active star formation. Gas clouds moving into the denser region of an arm experience a compression that can push them past the threshold needed to begin collapsing under their own gravity. The arm is, in a sense, a trigger, a place where the conditions for star formation are met more readily than in the quieter interarm regions. The result is a concentration of newly formed stars that makes the arm visually bright, even though its underlying stellar population is not dramatically more dense than the regions around it. The Milky Way's spiral structure also reflects its classification as a barred spiral galaxy. Rather than arms emerging directly from a rounded central bulge, as in some spiral galaxies, our galaxy's arms emerge from the ends of a bar-shaped structure that runs through the galactic center. This bar is composed of older stars and extends perhaps 27,000 light-years from end to end, oriented at an angle to our line of sight. The arms connect to the ends of this bar and wind outward from there, giving the galaxy a somewhat different appearance than an unbarred spiral would have when viewed from above. The bar itself was not confirmed observationally until the 1990s and early 2000s, when infrared surveys of the Galactic Center provided the stellar density maps needed to trace its outline. It had been suspected for some time based on the behavior of gas in the central regions, which showed velocity patterns consistent with motion around a bar rather than a simple circular center. But the direct evidence took decades to accumulate. Even now, the exact dimensions and orientation of the bar continue to be refined as new data arrives. Mapping the full extent of the spiral arms has been one of the ongoing projects of galactic astronomy. Radio observations of hydrogen gas provided the first large-scale maps. Later, surveys of specific types of objects that serve as distance markers, young star clusters, star-forming regions, certain classes of variable stars, added detail and precision. The Gaia mission has contributed enormously to this work by providing accurate distances to vast numbers of individual stars, allowing astronomers to trace the three-dimensional structure of the arms with far greater precision than was previously possible. What has emerged from all of this work is a picture of a galaxy whose spiral structure is real and measurable, but also somewhat irregular. The arms are not perfectly symmetric, perfectly spaced, or perfectly smooth. They branch and fragment in places. Their pitch angles, the angle at which they wind outward from the center, vary from arm to arm and along the length of individual arms. The galaxy has the broad character of a grand design spiral, meaning its arms are coherent over large scales, but the fine details show the complexity of a structure that has evolved over billions of years through star formation, stellar death, gravitational interactions, and the accretion of smaller galaxies. Our own position in one of the smaller spurs of this system is, in its own way, a comfortable place to be. We sit in a region of moderate stellar density, away from the intense activity of the Galactic Center, and not so far out in the disk that the surrounding stars are sparse. The Orion Arm is a quiet neighborhood in a large and complex city, and from here the rest of the structure extends outward in every direction, most of it too far away to visit, and much of it still being mapped. Chapter 4. The Galactic Center. At the heart of the Milky Way lies a region unlike anything in our immediate cosmic neighborhood. It is a place of extreme density, intense radiation, and gravitational forces that dwarf anything experienced in the quiet outer regions of the disk where our Sun resides. The Galactic Center is not somewhere we can visit or even observe easily, but it has been studied with increasing detail over the past several decades, and what astronomers have found there has deepened our understanding of how galaxies are structured and how they evolve over time. The Galactic Center lies approximately 26,000 light-years from our solar system, in the direction of the constellation Sagittarius. That distance is large enough that the center is completely invisible in ordinary optical light. The intervening space between us and the center is filled with dust clouds that absorb and scatter visible wavelengths almost completely. If you pointed an optical telescope directly toward the galactic center, you would see a rich field of nearby stars and dark patches of obscuring dust, but nothing of the center itself. The dust acts as an opaque curtain drawn across one of the most dramatic regions of the galaxy. To see through this curtain, astronomers have relied on wavelengths of light that dust does not block. Infrared radiation penetrates dust far more effectively than visible light, and radio waves pass through it almost entirely unimpeded. X-ray and gamma-ray observations conducted from space-based observatories above Earth's absorbing atmosphere have revealed high-energy processes occurring in the central region that would otherwise be completely hidden. By combining observations across many different wavelengths, astronomers have assembled a detailed picture of the galactic center that no single type of observation could provide alone. What this multi-wavelength picture reveals is a region of remarkable complexity. The central few, 1,000 light-years of the galaxy contain a higher density of stars than anywhere else in the Milky Way. In the outer disk, where we live, stars are separated by distances of several light-years on average. Near the galactic center, stars are packed far more tightly, with separations that can be measured in fractions of a light-year rather than multiples of it. The night sky, as seen from a hypothetical planet near the galactic center, would look nothing like our own. It would be blazing with the combined light of stars so numerous and so close together that darkness would be difficult to find. Embedded within this dense stellar environment is a structure called the Central Molecular Zone, a region of dense gas and dust extending several hundred light-years from the center. This zone contains a significant fraction of the galaxy's total supply of dense molecular gas, the raw material from which stars form. Star formation activity in the Central Molecular Zone is complex and somewhat different from the star formation that occurs in the spiral arms of the outer disk. The extreme conditions near the center, higher temperatures, stronger radiation fields, more intense gravitational forces, alter the way gas clouds behave and the kinds of stars that form from them. Closer to the center still is a dense cluster of stars known as the nuclear star cluster. This is one of the most massive and densely packed stellar systems known anywhere in the universe, containing tens of millions of stars within a region just a few tens of light years across. The stars of the nuclear star cluster include both old, reddish stars that have been there for billions of years and younger, more massive stars, whose presence near the galactic center is something of a puzzle. Forming massive stars in such an extreme environment requires conditions that are not fully understood, and the presence of these young stars so close to the galactic center has been a subject of considerable scientific attention. At the very center of all of this, occupying a region smaller than our solar system, is the object that anchors the entire galaxy gravitationally. It is a supermassive black hole with a mass roughly 4 million times that of our Sun. Astronomers refer to it by the name Sagittarius A star, written as Sagittarius A with an asterisk, which reflects the radio source designation given to this region before its true nature was understood. The existence of this black hole was inferred long before it was directly confirmed through observations of the motions of stars in its vicinity. The key observations came from two independent teams of astronomers, one led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics, and the other by Andrea Ghez at the University of California, Los Angeles. Over the course of decades, both teams tracked the orbits of individual stars near the galactic center with extraordinary precision, watching them move on paths that could only be explained by the presence of an enormous concentration of mass in a very small volume. Some of these stars complete their orbits in as little as 15 to 20 years, moving at speeds of several thousand kilometers per second as they swing around the central mass. The orbits are elliptical, following the same gravitational rules that govern the orbits of planets around the Sun, just at vastly higher speeds and around a vastly more massive central object. The conclusion was unambiguous. Something with a mass of around 4 million suns was concentrated within a volume smaller than the distance from our Sun to its nearest neighboring star. No known collection of ordinary matter could be that compact. The object had to be a black hole. Genzel and Ghez shared the Nobel Prize in Physics in 2020 for this work, alongside Roger Penrose, who had contributed foundational theoretical work on black holes decades earlier. Direct visual confirmation of Sagittarius A star came in 2022, when the Event Horizon Telescope collaboration released an image of the black hole's shadow. The Event Horizon Telescope is not a single instrument, but a network of radio telescopes distributed around the world, linked together to function as a single telescope, with a resolution equivalent to that of an instrument the size of Earth. The image showed a bright ring of glowing gas surrounding a dark central region, the shadow cast by the black hole against the light of infalling material. It was a quiet but significant moment in astronomy, the first direct visual evidence of the object that has sat at the center of our galaxy for billions of years. Sagittarius A star is, by the standards of supermassive black holes, relatively quiet. Many galaxies harbor central black holes that are actively consuming large quantities of gas and radiating enormous amounts of energy in the process. These are called active galactic nuclei, and some of them outshine the entire rest of their host galaxy. Our own galactic center is not in such an active state. Sagittarius A star consumes material slowly and irregularly, producing flares of X-ray and infrared emission from time to time, but nothing like the sustained brilliance of an active nucleus. There is evidence that the Galactic Center was considerably more active in the past, perhaps a few million years ago, when a larger quantity of gas may have been falling into the black hole. But today, it is relatively calm, a sleeping giant at the heart of a quietly rotating galaxy. The region surrounding the central black hole also contains evidence of past energetic events on a much larger scale. Observations with gamma-ray telescopes have revealed enormous structures extending above and below the plane of the galaxy, sometimes called the Fermi bubbles, after the space telescope that first detected them clearly. These bubbles extend roughly 25,000 light-years above and below the galactic plane and appear to be the remnant of a period of intense activity centered on the galactic nucleus, possibly a massive outflow of material driven by a burst of star formation, or by a period when the central black hole was consuming gas at a much higher rate. The bubbles are still there, slowly fading, a record written in high-energy radiation of something that happened long ago at the center of our galaxy. All of this, the dense star clusters, the molecular gas, the supermassive black hole, the ancient energy structures, is packed into a region that, while vast by human standards, represents only a tiny fraction of the galaxy's total volume. The Galactic Center is the engine and anchor of the Milky Way, the point around which everything else orbits, and it has a history and a character entirely its own. From our quiet position, 26,000 light-years away, we observe it only indirectly, through wavelengths of light that can slip past the intervening dust. But even those indirect observations have revealed something extraordinary at the core of the structure we call home. Chapter 5. Our position in the galaxy. There is something worth pausing on before we continue outward through the galaxy's structure. We have been describing the Milky Way as though from a distance, tracing its disk and its arms and its central regions, as an observer might trace the features of a map. But we are not outside observers. We are participants. Our Sun, and every planet orbiting it, and everything that has ever lived on any of those planets, exists at a specific location within this structure. That location has consequences for what we can see, for the environment we inhabit, and for the history that brought us here. The Sun sits in the disk of the Milky Way, roughly 26,000 light-years from the Galactic Center. This figure has been refined considerably over the decades. Early estimates place the center at distances ranging from around 30,000 to over 50,000 light-years, with significant uncertainty. Modern measurements, particularly those made possible by precise radio observations of the Galactic Center region and by the stellar orbit studies that confirm the existence of Sagittarius A star, have converged on a value close to 26,000 light-years, sometimes stated as 26 to 27,000 light-years, depending on the measurement method used. This distance places our Sun in what might be described as the middle suburbs of the galaxy. We are not near the center, where stellar density is high and conditions are more extreme. We are not in the outermost reaches of the disk, where stars become sparse and the galaxy fades toward emptiness. We sit at an intermediate distance, in a region of the disk that is reasonably well populated with stars, gas, and dust, but not so crowded as to create a dramatically different environment from what we experience today. Our position relative to the spiral arms is also worth describing carefully. As mentioned in the previous chapter, the Sun does not currently sit within one of the four major spiral arms. It lies in the Orion Arm, a smaller spur of denser material positioned between the Perseus arm, which lies further from the Galactic Center, and the Sagittarius arm, which lies closer to it. The Sun is currently near the inner edge of the Orion arm, having passed through the arm's denser regions in the relatively recent past in astronomical terms. Because stars and gas clouds orbit the galaxy at slightly different speeds than the spiral arm pattern moves, our Sun has spent different parts of its history in different positions relative to the arms, sometimes within a major arm, and sometimes in the quieter interarm regions. This movement in and out of spiral arms over the Sun's lifetime is thought to have had real consequences for conditions in our solar system. The spiral arms are regions of active star formation, which means they contain a higher density of massive young stars that end their lives in supernova explosions. A supernova in the relatively near vicinity of our solar system could have significant effects, potentially disrupting the Oort cloud of distant comets, increasing the flux of cosmic rays reaching the inner solar system, or in extreme cases affecting conditions on Earth's surface. The periods during which our Sun was passing through or near a major spiral arm may have coincided with periods of increased bombardment or other environmental changes. This connection between the solar system's galactic journey and conditions on Earth is an area of ongoing research, with some intriguing correlations identified, but the causal relationship still being worked out. The Sun also has a vertical position within the disk that is worth noting. The galactic plane, the midplane of the disk, where the average density of material is highest, does not pass exactly through the Sun. Our solar system sits a modest distance above the midplane, currently estimated at somewhere between 50 and 100 light-years north of it, using the conventional astronomical direction for north in galactic coordinates. The Sun oscillates gently above and below the midplane over time, carried by the gravitational pull of the disk's material in a slow bobbing motion with a period of roughly 30 to 40 million years. At the moment, we are slightly above the midplane and moving further above it, before gravity will eventually pull us back down and through to the other side. This gentle oscillation means that our solar system has experienced both sides of the galactic midplane many times over its history. The midplane is where the densest concentrations of gas and dust are found, so passages through it represent periods of slightly denser surrounding environment. Some researchers have proposed that these crossings of the midplane might correlate with periods of increased cometary bombardment or other disturbances to the outer solar system, though establishing firm causal links across such vast timescales is difficult. The overall motion of the Sun through the galaxy combines this vertical oscillation with the primary orbital motion around the galactic center. At approximately 230 kilometers per second, the Sun traces a path around the center that is not perfectly circular. Like most stars in the disk, it follows a slightly elliptical orbit, moving a bit faster when closer to the center and a bit slower when further away. Superimposed on this are small perturbations from the gravitational influence of nearby stars and passing molecular clouds. The result is a path through the galaxy that is broadly circular but imprecise in its details, a long, slow spiral through the disk that has carried our solar system through many different neighborhoods over its 4.5 billion year history. It is worth considering what our position means for our ability to observe the universe. In some ways, being in the outer disk of a spiral galaxy is disadvantageous for astronomy. The plane of the disk, as seen from our position within it, creates the broad band of the Milky Way that fills much of the sky, and the dust concentrated in the disk blocks our view of objects lying in that direction. a significant fraction of the sky is difficult or impossible to observe in visible light because of this obscuration. Regions behind the galactic center are particularly challenging, and there is even a term for the region of sky most heavily affected, the zone of avoidance, referring to the broad swath of sky around the galactic plane where the density of observed external galaxies drops dramatically because dust prevents us from seeing them. On the other hand, our position in a relatively quiet part of the outer disk gives us a stable environment that has persisted for long enough to allow the development of complex chemistry, planetary systems, and life. The galactic center is a far more energetic and variable environment. Regions near active star formation zones experience higher rates of supernova explosions and more intense radiation fields. Our neighborhood, by contrast, is calm and has been calm for a very long time. The Sun has orbited the galaxy approximately 20 times since it formed, and throughout that journey, it has inhabited a part of the disk where conditions have been broadly stable and conducive to the slow, patient processes that produce the world we know. There is a certain quietness to our galactic address that is easy to overlook. 26,000 light-years from the center, in a minor spur between two spiral arms, slightly above the mid-plane, in one of hundreds of billions of star systems distributed through the disk. Nothing about our location is remarkable by galactic standards. We are not near anything particularly unusual. We occupy an ordinary stretch of an ordinary galaxy, and from that ordinary vantage point, we have spent the past few centuries gradually piecing together the true scale and structure of the place we inhabit. That ordinariness, on reflection, is remarkable in its own way. The universe does not appear to have arranged things so that observers find themselves in special or privileged locations. We are where we are because a cloud of gas collapsed here, in this part of this galaxy, at this moment in cosmic history, and the conditions were right for what followed. Our position in the Milky Way is not the center of anything. It is simply where things happen to unfold. Chapter 6. The Galactic Halo. When most people picture the Milky Way, they picture the disk, the flat, rotating structure of stars and gas and dust that we have been exploring in the previous chapters is the most visible and most familiar part of the galaxy, and it is where the vast majority of the stars we can see with the naked eye are located. But the disk is not the whole galaxy. Surrounding it, extending far above and below the plane and outward beyond the edge of the disk in every direction, is a much larger and much less visible structure called the halo. The halo is not empty. It contains stars, though far fewer of them than the disk, distributed in a roughly spherical volume that extends to distances several times greater than the diameter of the disk itself. It contains globular clusters, those ancient dense balls of stars that Harlow Shapley used a century ago to establish the Sun's distance from the galactic center. It contains thin streams of stars, the disrupted remnants of smaller galaxies that have been pulled apart by the Milky Way's gravity over billions of years. And it contains, in quantities that dwarf everything else, a form of matter that emits no light and reveals itself only through its gravitational effects. We will come to that in the next chapter. For now, the stellar halo and its visible contents deserve attention of their own. The stellar halo of the Milky Way is old. The stars found in the halo are among the oldest in the galaxy, many of them forming in the very earliest phases of the Milky Way's assembly more than 10 billion years ago. They are poor in heavy elements relative to younger stars like our Sun, because they formed at a time when the universe had not yet produced large quantities of elements heavier than hydrogen and helium through stellar nucleosynthesis. The composition of halo stars carries a record of the conditions that existed in the very early universe, and studying them provides a window into the galaxy's distant past that cannot be obtained any other way. The orbits of halo stars are very different from the orbits of disk stars. Stars in the disk orbit the galactic center in the same direction, in roughly circular paths that keep them close to the plane. This ordered, co-rotating motion is what gives the disk its flat, structured appearance. Halo stars, by contrast, follow orbits that are tilted at all angles to the disk, some of them highly elliptical, some of them retrograde, moving in the opposite direction to the disk's rotation. This chaotic mix of orbital orientations gives the halo its roughly spherical shape. At any given moment, halo stars are distributed throughout a large volume surrounding the disk, moving in all directions, passing through the disk periodically before swinging back out into the halo. The globular clusters of the halo are perhaps its most spectacular visible inhabitants. The Milky Way is thought to host somewhere between 150 and 200 globular clusters, though the exact count is uncertain because some may be hidden behind the dust of the galactic plane. Each cluster is a gravitationally bound system of stars, ranging from perhaps 100,000 to several million members, packed into a roughly spherical volume typically between 10 and 300 light-years across. The stars within a globular cluster are extraordinarily close together by the standards of the disk. At the center of a dense globular cluster, the nearest neighboring star might be only a fraction of a light-year away, compared to the several light-years that typically separate stars in our part of the disk. Globular clusters are old. Most of them formed in the early universe, more than 10 billion years ago, and they have survived largely intact ever since. They are, in a sense, fossils of the early galaxy, collections of ancient stars that have been orbiting the galactic center together for most of the history of the universe. Their ages can be estimated by studying the properties of the stars they contain, and those estimates consistently place the oldest globular clusters at ages of 12 to 13 billion years, not far short of the age of the universe itself. Not all globular clusters formed within the Milky Way. Some of them are thought to be the remnant cores of smaller galaxies that were captured by the Milky Way and gradually disrupted. As a smaller galaxy falls into a larger one, the gravitational tidal forces of the larger galaxies stretch and pull the smaller one apart, dispersing its stars into long streams that wrap around the host galaxy. If the smaller galaxy had a particularly dense central region, that region may survive the disruption as a globular cluster-like object, continuing to orbit within the halo of its captor long after the rest of its parent galaxy has been dispersed. These stellar streams, the dispersed remnants of captured galaxies, are one of the most striking features revealed by modern surveys of the halo. The Sagittarius dwarf galaxy, a small galaxy currently in the process of being absorbed by the Milky Way, has left an enormous stream of stars wrapping multiple times around the entire galaxy. This Sagittarius stream can be traced across a large fraction of the sky, a ghostly river of stars marking the path that the dwarf galaxy has followed as it has been gradually torn apart by our galaxy's gravity. Other streams have been identified as well, some of them associated with known dwarf galaxies and others of uncertain origin, their parent galaxies having been so thoroughly disrupted that little remains to identify them. The existence of these streams tells us something important about the Milky Way's history. The galaxy did not form in isolation, fully assembled from the beginning. It grew over time through the accumulation of smaller structures, pulling in dwarf galaxies and star clusters and loose associations of stars. incorporating their material into its own body. This process of hierarchical assembly is thought to be the standard way that large galaxies form in the universe, growing gradually through mergers and accretion, rather than appearing fully formed. The streams and disrupted remnants visible in the halo today are the evidence of that long history of growth, the archaeological record of the galaxy's formation, written in the positions and motions of ancient stars. The halo extends to considerable distances. The stellar halo, the visible component populated by individual stars and globular clusters, reaches out to perhaps 100 to 150,000 light-years from the galactic center, roughly comparable to the diameter of the disk. But there are hints that some structures associated with the halo extend even further. Certain stellar streams and collections of stars have been found at distances of 200,000 light-years or more, suggesting that the outermost reaches of the galaxy's stellar component are more extensive than previously appreciated. Beyond even these outermost stars, the gravitational influence of the Milky Way continues. The galaxy's gravity shapes the orbits of objects at vast distances, including its satellite galaxies, which orbit at distances of hundreds of thousands of light-years. The boundary of the galaxy, in the gravitational sense, is not defined by where the last star is found, but by where the Milky Way's gravity gives way to the gravity of other structures. That boundary lies much further out than the visible stars, in a region dominated not by any form of light-emitting matter, but by the dark matter halo that encompasses and exceeds everything we can see. The halo, in this sense, is a reminder that galaxies are more than their visible parts. The disk of stars and gas that we picture when we think of the Milky Way is embedded within and surrounded by a much larger structure, most of which gives off no light at all. To understand the true scale of the galaxy, we need to consider not just what we can see, but what the behavior of what we can see tells us about what we cannot. Chapter 7. Dark Matter and the Invisible Structure. There is more to the Milky Way than can be seen. This is not a vague philosophical observation, but a precise scientific conclusion, arrived at through careful measurement and repeated across many different lines of evidence. The visible components of the galaxy, the stars, the gas, the dust, the globular clusters, the stellar streams, account for only a fraction of the total mass that the galaxy's gravitational behavior requires. The rest is something else, something that does not emit light, does not absorb light, and reveals itself only through the gravitational pull it exerts on everything around it. Astronomers call it dark matter, and understanding it is essential to understanding the true scale and structure of the Milky Way. The first hints that galaxies might contain more mass than their visible stars could account for came in the 1930s, when Swiss astronomer Fritz Zwicky studied the motions of galaxies within a large cluster and found that they were moving far too fast to be held together by the gravity of the visible matter alone. Something extra was needed to keep the cluster from flying apart. Zwicky proposed that the cluster contained large amounts of unseen mass, which he called dunkle materie, dark matter. His conclusion was largely ignored at the time, considered an anomaly rather than a fundamental insight. The case for dark matter became much harder to ignore in the 1970s, when American astronomer Vera Rubin and her colleague Kent Ford measured the rotation curves of spiral galaxies. A rotation curve is simply a plot of how far stars orbit their galaxy's center as a function of their distance from that center. Based on the distribution of visible matter, the expectation was clear. Stars near the center of a galaxy where most of the visible mass is concentrated, should orbit quickly. Stars further out, in the less densely populated outer disk, should orbit more slowly, just as the outer planets of our solar system move more slowly than the inner ones. This declining rotation speed with increasing distance was the expected pattern. What Rubin and Ford found was something entirely different. The rotation curves of spiral galaxies were flat. Stars in the outer regions of galaxies were moving just as fast as stars near the center, sometimes faster. The orbital speeds did not decline with distance. They remained roughly constant across the entire observable extent of the disk and beyond. This flatness was incompatible with the visible mass distribution. To produce flat rotation curves, there had to be additional mass distributed throughout and beyond the disk, a mass distribution that increased roughly in proportion to the distance from the center, keeping the orbital speeds constant as they would be in the presence of such a distribution. The conclusion was that spiral galaxies are embedded within enormous halos of unseen mass, extending far beyond their visible disks. These dark matter halos are not concentrated in the plane of the disk. They are roughly spherical, surrounding the entire visible galaxy in a vast cloud that provides the gravitational scaffolding within which the disk rotates. The flat rotation curves observed by Rubin and Ford, and subsequently confirmed for galaxy after galaxy, are the clearest direct evidence for the existence of dark matter halos around spiral galaxies. The Milky Way is no exception. Our galaxy's rotation curve has been measured by tracking the motions of stars, gas clouds, and other objects at various distances from the galactic center, and it shows the same characteristic flatness seen in other spiral galaxies. The orbital speeds remain high far out into the disk and beyond, requiring the presence of a dark matter halo that extends to distances well beyond the visible stellar disk. Estimating the total mass of the Milky Way's dark matter halo is not straightforward, because dark matter by definition does not show up directly in any observation. Instead, its mass must be inferred from its gravitational effects. Several methods are used. One involves measuring the velocities of objects at large distances from the galactic center, satellite galaxies, globular clusters, hypervelocity stars, and calculating what total mass would be needed to produce those motions. Another involves modeling the dynamics of satellite galaxy orbits. Another involves gravitational lensing, the deflection of light from background objects by the mass of the galaxy. These different methods give somewhat different results, and the total mass of the Milky Way has been a subject of ongoing debate and refinement. Recent estimates place the total mass of the galaxy, visible matter plus dark matter halo, at somewhere between 500 billion and 1.5 trillion times the mass of the Sun. The visible stellar component, by comparison, accounts for perhaps 50 to 60 billion solar masses. The difference between the total mass and the visible mass represents the dark matter, which outweighs the visible matter by a factor of roughly 10 to 1 or more. The dark matter halo extends to distances far beyond the visible galaxy, while the stellar disk has a diameter of around 100,000 light-years, and the stellar halo extends perhaps 100 to 150,000 light-years. The dark matter halo is thought to reach out to perhaps 300,000 to 600,000 light-years from the galactic center, with considerable uncertainty in the outer regions where measurements become increasingly difficult. The true boundary of the Milky Way, if we define it as the extent of the dark matter halo, is therefore several times larger than the visible galaxy alone. This has a profound effect on how we think about the size of the Milky Way. When we say the galaxy is 100,000 light-years across, we are describing only the visible disk. The full extent of the gravitational structure within which that disk is embedded is considerably larger, perhaps 3 to 6 times larger, depending on how the boundary is defined. The disk of stars that we can see and photograph is, in a sense, just the bright tip of a much larger and mostly invisible structure. What dark matter actually is remains one of the most important open questions in physics. It is not ordinary matter in a dark form, not black holes, not burned-out stars, not cold gas clouds. These possibilities have been explored and largely ruled out as the dominant component of dark matter. The evidence strongly suggests that dark matter is a new type of particle, one that doesn't interact with light or with ordinary matter through any of the known forces except gravity. Various candidate particles have been proposed by theoretical physicists with names like WIMPs, weakly interacting massive particles, and axions, but none has yet been directly detected in a laboratory. Experiments designed to catch dark matter particles passing through detectors deep underground have so far produced no confirmed signals, though they continue to operate and improve in sensitivity. The situation is scientifically unusual. We have strong, multiply confirmed evidence for the existence of something that makes up the majority of the mass of galaxies, that shapes the large-scale structure of the universe, and that has been present since the earliest moments of cosmic history. And yet, we do not know what it is. Dark matter is one of the clearest examples of a gap in our understanding that is defined not by ignorance, but by very precise knowledge of what we do not know. We know how much of it there is, roughly. We know how it is distributed. We know how it behaves gravitationally. We just do not know what it is made of. For the Milky Way, the practical consequence of dark matter is that the galaxy is considerably more massive and considerably more spatially extended than its visible components alone would suggest. The dark matter halo is the dominant structural component of the galaxy by mass, providing the gravitational framework within which the disk formed and within which it continues to rotate. Without it, the disk could not maintain its structure. The spiral arms would not wind in the way they do. The satellite galaxies would follow different orbits. The Milky Way, as we know it, is, in a real sense, a creation of its dark matter halo, as much as it is a creation of the stars and gas that we can actually see. This invisible architecture, stretching hundreds of thousands of light years in every direction from the Galactic Center, is the true outer boundary of our galaxy. It is vast, it is ancient, and it is almost entirely unknown in its physical nature. The disk of stars embedded within it is, by comparison, a thin and luminous shell of activity, bright and beautiful against the dark backdrop of something far larger and far more mysterious. Chapter 8. Satellite Galaxies. The Milky Way does not travel through the universe alone. Surrounding it, bound to it by gravity, orbiting it at various distances and on various timescales, is a collection of smaller galaxies. These are the satellite galaxies of the Milky Way, and they represent an important part of the full picture of our galaxy's extent and its place in the broader cosmic environment. Some of them are close enough to be visible to the naked eye from the southern hemisphere. Others are so faint and diffuse that they were only discovered within the past few decades, and new ones continue to be found as survey technology improves. The two most prominent satellite galaxies are the Large Magellanic Cloud and the Small Magellanic Cloud. These are irregular dwarf galaxies, meaning they lack the ordered spiral or elliptical structure of larger galaxies and have a somewhat chaotic, patchy appearance. And they are visible from the southern hemisphere as two detached patches of the Milky Way, glowing softly in the night sky. They were well known to peoples of the southern hemisphere long before European astronomers documented them, and they were named after the Portuguese explorer Ferdinand Magellan, following his circumnavigation of the globe in the early 16th century, during which European sailors encountered them as prominent features of the southern sky. The large Magellanic Cloud lies at a distance of approximately 160,000 light-years from our solar system, placing it well outside the visible stellar disk of the Milky Way, but within the extended dark matter halo we discussed in the previous chapter. It is itself a substantial galaxy, containing somewhere between 10 and 30 billion solar masses of material and spanning roughly 14,000 light-years across its main body. It contains active star-forming regions, including the Tarantula Nebula, one of the most intensely star-forming regions known in the local group of galaxies. If the Tarantula Nebula were as close to us as the Orion Nebula, it would cast shadows on the ground at night. The small Magellanic Cloud sits at a similar distance, roughly 200,000 light-years away, and is smaller than its companion, containing a few billion solar masses of material. Both Magellanic Clouds are irregular in shape, though the large Magellanic Cloud shows hints of a bar structure suggesting it may once have been a barred spiral galaxy before gravitational interactions disrupted its form. The two clouds are connected to each other and to the Milky Way by a structure called the Magellanic Stream, a long ribbon of gas stretching across a significant portion of the sky, pulled out from the clouds by tidal forces as they orbit our galaxy. The Magellanic Stream is one of the largest structures associated with the Milky Way system, extending over more than 140 degrees of sky as seen from Earth. Whether the Magellanic Clouds are long-term companions of the Milky Way or relatively recent arrivals is a question that has been debated. Measurements of their velocities suggest they may be moving fast enough to be on their first close approach to the Milky Way, rather than having orbited it many times. If this is correct, they have not always been our nearest galactic neighbors. They may have spent most of their history in a more distant part of the universe before falling into the Milky Way's gravitational influence relatively recently in cosmic terms. Their eventual fate is likely absorption into the Milky Way itself, over a timescale of several billion years, their stars and gas becoming part of our galaxy's disk and halo. Beyond the Magellanic Clouds, the Milky Way is surrounded by a larger population of smaller, fainter dwarf galaxies. Many of these are dwarf spheroidal galaxies, small, roundish collections of old stars with very little gas or current star formation, held together by gravity but contributing little visible light relative to their mass. They are among the faintest galaxies known, some of them containing only a few thousand to a few million stars, spread across a volume comparable in size to the Milky Way's disk, but containing a tiny fraction of its stellar mass. For a long time, only a handful of these dwarf satellites were known. The first confirmed dwarf satellites beyond the Magellanic Clouds were identified in the mid-20th century. The Sculptor Dwarf Galaxy and the Fornax Dwarf Galaxy, both discovered in the late 1930s, were among the earliest recognized members of this population. By the end of the 20th century, around a dozen dwarf satellite galaxies of the Milky Way had been confirmed. Then came the digital sky surveys. Beginning in the early 2000s, large-scale systematic surveys of the sky using sensitive digital detectors began finding dwarf galaxies that had been too faint to detect with earlier technology. The Sloan Digital Sky Survey, which mapped a large portion of the northern sky in multiple wavelengths, revealed numerous new satellite galaxies that had previously been completely unknown. These ultra-faint dwarf galaxies are extraordinarily dim, some of them having a total luminosity less than that of a single bright star cluster, spread across a volume comparable to or larger than the Magellanic Clouds. They are detectable only through careful statistical analysis of the positions of individual stars, looking for overdensities that suggest a bound system rather than a random distribution of background stars. The current count of confirmed and candidate satellite galaxies of the Milky Way stands at somewhere between 50 and 60, though this number continues to grow with each new survey. More importantly, theoretical models of galaxy formation predict that a galaxy the size of the Milky Way should be surrounded by many more satellite galaxies than have been observed, possibly hundreds or even thousands of small dark matter halos that should contain at least some stars. The discrepancy between the predicted number of satellites and the observed number has been called the missing satellites problem, and it has been one of the persistent puzzles of galaxy formation theory for several decades. Several explanations have been proposed. One possibility is that many of the predicted small dark matter halos do exist, but contain so few stars that they are effectively invisible with current technology. They may be dark galaxies, structures with the gravitational signature of a galaxy, but no detectable stellar content. Another possibility is that the processes of galaxy formation are less efficient at small scales than theoretical models predict, so that many small dark matter halos never accumulated enough gas to form stars in the first place. A third possibility involves the effects of Ryanization, the period in cosmic history when the first stars and galaxies flooded the universe with ultraviolet radiation, which could have heated and dispersed the gas in small halos before it had a chance to collapse into stars. The distribution of the known satellite galaxies around the Milky Way has also attracted attention. Rather than being distributed randomly in all directions, as would be expected if they had fallen in independently from random directions, many of the satellite galaxies appear to lie in a flattened plane, sometimes called the vast polar structure, or the plane of satellites. This structure is oriented roughly perpendicular to the disk of the Milky Way and contains a significant fraction of the known satellites, many of them co-rotating within this plane. A similar planar arrangement of satellites has been found around the Andromeda Galaxy. The origin of these planar structures is not well understood and presents a challenge to standard models of galaxy formation, which generally predict a more isotropic distribution of satellite orbits. The satellite galaxies of the Milky Way are not merely interesting objects in their own right. They are also probes of the dark matter distribution in the outer reaches of our galaxy. Their orbits, their internal dynamics, and their survival or disruption over cosmic time all depend on the gravitational environment in which they move, which is dominated by dark matter. Studying them provides constraints on the mass and extent of the Milky Way's dark matter halo that complement other measurement methods and help build a more complete picture of our galaxy's true dimensions. Taken together, the satellite system of the Milky Way extends our galaxy's sphere of influence to distances of several 100,000 light-years, with the most distant confirmed satellites lying at distances of around 1 million light-years or more from the Galactic Center. At these distances, the boundary between what belongs to the Milky Way and what belongs to the broader local group of galaxies becomes genuinely ambiguous. The galaxy does not end cleanly. It fades and blurs into the larger structure of which it is a part, its influence gradually giving way to the collective gravity of everything around it. Chapter 9. the local group. The Milky Way is a large galaxy. We have spent several chapters establishing just how large, tracing its disk and its halo and its satellite system outward to distances of hundreds of thousands of light years. And yet, for all its size, the Milky Way is not alone in its immediate region of the universe. It belongs to a collection of galaxies bound together by mutual gravity, a grouping that astronomers call the local group. Understanding the local group is the next step in placing our galaxy in its proper cosmic context, because the Milky Way's dimensions and character can only be fully appreciated when seen alongside the other members of the family it inhabits. The local group spans a volume of space roughly 10 million light-years across. Within that volume, there are approximately 80 confirmed member galaxies, though the count continues to rise as surveys reveal new dwarf galaxies too faint to have been detected previously. The membership ranges enormously in scale. At one end are the two dominant spiral galaxies that between them contain the vast majority of the group's stellar mass. At the other end are tiny dwarf galaxies with only a few million stars, barely distinguishable from large star clusters and detectable only through careful modern surveys. The two dominant members of the local group are the Milky Way and the Andromeda Galaxy. These two spiral galaxies are the heavyweights of the group, each containing hundreds of billions of stars and each surrounded by its own collection of satellite galaxies. They are separated by a distance of approximately 2.5 million light-years, a number that sounds comfortably large, but is, in the context of galactic dynamics, close enough for the two galaxies to be gravitationally bound to each other and to be approaching one another. The Andromeda Galaxy, known by its catalogue designation Messier 31, or simply M31, is the nearest large spiral galaxy to the Milky Way and is visible to the naked eye on a clear, dark night as a faint smudge in the constellation Andromeda. It is the most distant object routinely visible to the unaided human eye, its light having travelled for approximately 2.5 million years before reaching us. What we see when we look at Andromeda is not the galaxy as it exists today, but as it existed 2.5 million years ago, when our own ancestors were early hominids living on the African savanna. Andromeda is somewhat larger than the Milky Way in terms of its stellar disk, spanning perhaps 200,000 light-years across its disk compared to the Milky Way's 100,000. For a long time, it was thought to be significantly more massive than the Milky Way as well, but more recent measurements of both galaxies' total masses, including their dark matter halos, have produced results that are surprisingly similar, and in some analyses favour the Milky Way as the slightly more massive of the two. The comparison depends significantly on the measurement method used, and on the assumptions made about the extent of each galaxy's dark matter halo. And the question of which galaxy is more massive has not been definitively settled. Andromeda has its own extensive satellite system. Its two largest satellites, Messier 32 and Messier 110, are visible in the same field of view as Andromeda itself through a small telescope. Beyond these, Andromeda is surrounded by numerous dwarf galaxies, many of them arranged in a planar structure similar to the one observed around the Milky Way. The total number of confirmed Andromeda satellites is comparable to the number around the Milky Way, suggesting that the two galaxies have had broadly similar histories of satellite accretion. The third significant member of the local group is the Triangulum Galaxy, also known as Messier 33. This is a smaller spiral galaxy located roughly 3 million light-years from us, somewhat further than Andromeda, and containing perhaps 40 billion solar masses of stars. It is the third largest member of the local group by stellar mass, and is a relatively undisturbed, loosely wound spiral with active star formation. Whether it is a satellite of Andromeda or an independent member of the local group on its own orbit is a matter of ongoing discussion, with some evidence suggesting it is falling toward Andromeda for the first time. The remaining members of the local group are overwhelmingly dwarf galaxies of various types. Some are dwarf irregulars, like the Magellanic Clouds, with patchy star formation and irregular shapes. Others are dwarf spheroidals, old and gas-poor, their star formation having ended billions of years ago. A few are dwarf ellipticals, slightly more massive and more smoothly distributed than the spheroidals. Many of these smaller galaxies are satellites of either the Milky Way or Andromeda, their orbits carrying them within the gravitational spheres of influence of the two dominant spirals. Others may be more isolated members of the group, following orbits that carry them through the space between the two major galaxies. The dynamics of the local group are dominated by the gravitational interaction between the Milky Way and Andromeda. Despite the general expansion of the universe, which carries most galaxies away from one another, the Milky Way and Andromeda are moving toward each other. The expansion of space is not strong enough at these distances to overcome the mutual gravitational attraction between two large galaxies separated by only a few million light-years. Current measurements of Andromeda's velocity place it approaching the Milky Way at roughly 110 kilometers per second along the line of sight, with some additional sideways motion that makes the precise details of the future encounter uncertain. The best current models of the collision suggest that the two galaxies will begin their first close approach in roughly 4 to 5 billion years. At that point, the disks of the two galaxies will interpenetrate, their stars passing through one another, not colliding directly, since the distances between individual stars are so vast that actual stellar collisions would be extremely rare, but their gravitational fields interacting in complex ways that will dramatically distort the shapes of both galaxies. Gas clouds will collide and compress, triggering bursts of star formation. The spiral structures of both galaxies will be disrupted. Over a timescale of perhaps a billion years following the first encounter, the two galaxies will merge into a single, larger system, most likely an elliptical galaxy or a large spheroidal galaxy, without the ordered disk structure that both currently possess. This future merger is sometimes described in dramatic terms, but it is worth noting that for any inhabitants of either galaxy at that time, the experience would be extraordinarily slow and gradual. The merger will unfold over hundreds of millions to billions of years, a timescale so vast that no individual or civilization could observe more than an infinitesimal fraction of it. The night sky would change over those immense timescales, new stars becoming visible, the shapes of familiar structures shifting, but nothing would happen quickly by any human measure of time. The local group as a whole is itself part of a larger structure. It sits near the outskirts of a much larger collection of galaxy groups and clusters called the Virgo supercluster, centered on the Virgo cluster of galaxies roughly 50 million light-years away. More recent mapping of cosmic structure has placed the local group within an even larger framework called Laniakea, a supercluster of galaxies spanning roughly 500 million light-years that contains the mass of approximately 100 million billion suns. Within Laniakea, the local group is a small and peripheral member, located near one of the outer filaments of the supercluster's complex web-like structure. The local group is thus both a home and a stepping stone. It is the immediate gravitational community of the Milky Way, the collection of galaxies that our galaxy interacts with most directly and whose future is most closely linked to our own. But it is also just one small node in a hierarchy of structures that extends outward across hundreds of millions and eventually billions of light years, each level of structure containing the levels below it and being contained by the levels above. From our position inside the Milky Way, looking outward through its disk and its halo, and across the 2.5 million light years to Andromeda, the local group represents the edge of what might reasonably be called our cosmic neighborhood. Beyond it, the universe continues in all directions, galaxy groups and clusters and superclusters stretching away to distances that make even the local group seem small. We will consider some of that broader context in later chapters. For now, the local group reminds us that even after tracing the Milky Way outward through its disk and halo and satellite system, there is still more structure to place it within, still more context needed before the full picture comes into view. Chapter 10. How we measure galactic distances. Everything we have discussed so far rests on a foundation of measurement. The diameter of the disk, the extent of the halo, the distance to the Galactic Center, the separation between the Milky Way and Andromeda. None of these numbers appeared fully formed. Each one was arrived at through a specific method, often refined over decades by multiple generations of astronomers working with progressively better instruments. Understanding how these distances are measured adds something important to the picture, because it reveals not just what the numbers are, but how we know them, and what the uncertainties in them actually mean. Measuring distances in astronomy is fundamentally different from measuring distances in everyday life. You cannot stretch a tape measure across space. You cannot send a signal and wait for it to return in any practical sense for distances beyond our immediate solar neighborhood. Instead, astronomers have developed a series of overlapping techniques, each valid over a certain range of distances that together form what is sometimes called the cosmic distance ladder. Each rung of the ladder depends on the rungs below it, calibrated by closer measurements and extended outward to reach further and further into space. The first and most direct rung of the ladder is parallax. This technique exploits a simple geometric principle. When you observe a nearby object from two different positions, it appears to shift slightly against the background of more distant objects. This apparent shift is called parallax, and its size depends on how far away the object is and how far apart the two observation points are. Hold a finger in front of your face and close one eye, then the other. Your finger appears to jump against the background. Move your finger further away, and the jump becomes smaller. The relationship between the size of the jump and the distance to the object is straightforward geometry. For nearby stars, astronomers use the diameter of Earth's orbit around the Sun as their baseline. Observing a star in January and again in July, when Earth is on the opposite side of its orbit, 6 months and 300 million kilometers away from its earlier position. The apparent shift of the nearby star against the background of much more distant stars is the parallax angle, and from it the distance can be calculated directly. The unit of distance, called the parsec, is defined by this method. 1 parsec is the distance at which a star would show a parallax shift of exactly 1 arcsecond, and it corresponds to approximately 3¼ light years. Parallax is the gold standard of astronomical distance measurement because it is purely geometric, requiring no assumptions about the physical properties of the object being measured. But it has a limitation. The parallax shifts of even relatively nearby stars are extraordinarily small, and as distance increases, the shifts become so tiny that they fall below the precision of any measurement instrument. From the ground, Parallax measurements are limited to distances of a few hundred light-years by the blurring effects of Earth's atmosphere. From space, where the atmosphere is no longer a problem, the precision improves dramatically. The Hipparcos satellite, launched in 1989, measured parallaxes for about 100,000 stars out to distances of a few thousand light-years with good precision. Its successor, the Gaia mission launched in 2013, has extended this to nearly 2 billion stars with far greater accuracy, measuring parallaxes reliably out to distances of tens of thousands of light-years. Gaia's measurements have transformed our knowledge of the three-dimensional structure of the galaxy, providing direct distance measurements for stars across a significant fraction of the disk, and enabling the mapping of spiral arm structure with unprecedented detail. Beyond the reach of direct parallax, astronomers rely on what are called standard candles. A standard candle is an object whose intrinsic brightness, the total amount of light it actually emits, is known from some independent measurement or physical understanding. If you know how bright something truly is, and you can measure how bright it appears from Earth, the difference between the two tells you the distance. A light bulb of known wattage appears dimmer the further away it is, and the relationship between true brightness, apparent brightness, and distance follows a precise mathematical rule. The same principle applies to astronomical objects. One of the most important classes of standard candles is the Cepheid variable star. Cepheids are stars that pulsate in a regular cycle, brightening and dimming over periods of days to weeks. In the early 20th century, Henrietta Swan Leavitt, working at the Harvard College Observatory, discovered a relationship between the period of a Cepheid's pulsation and its intrinsic luminosity. Cepheids that take longer to complete one cycle of brightening and dimming are genuinely more luminous than those with shorter periods. This period luminosity relationship means that simply by measuring how long a Cepheid takes to pulsate, you can determine how bright it truly is, and from there calculate its distance. Cepheid variables were the tool that Edwin Hubble used in 1923 to establish that the Andromeda Galaxy was far beyond the bounds of the Milky Way, settling the long-running debate about whether the spiral nebulae visible in the sky were objects within our own galaxy or separate island universes at great distances. Finding Cepheids in Andromeda and measuring their periods gave Hubble a distance estimate that placed Andromeda far outside any reasonable estimate of the Milky Way's size. The universe was suddenly much larger than most astronomers had previously supposed. Cepheids remain important distance indicators, used to calibrate the distance scale out to tens of millions of light-years. Within the Milky Way, they have been particularly valuable for mapping the structure of the disk. Because Cepheids are young, massive stars found in star-forming regions, they tend to trace the spiral arms where star formation is most active. Surveys of Cepheid variables across the galaxy have contributed significantly to our understanding of the disk's extent and the arrangement of its spiral structure. Another important class of standard candles is R Lyrae stars. These are older, less massive pulsating stars, fainter than Cepheids, but also following a period luminosity relationship. R Lyrae stars are found throughout the halo of the galaxy, including in globular clusters, making them useful for measuring distances to halo structures. They were important tools in Shapley's original work establishing the distance to the Galactic Center, and they continue to be used for mapping halo populations and satellite galaxies. At greater distances, other standard candles come into play. Type 1. A supernovae are among the most powerful distance indicators known, bright enough to be seen across billions of light-years. These are explosions that occur when a white dwarf star accumulates enough mass from a companion to trigger a runaway nuclear reaction. Because the trigger mechanism involves reaching a specific mass threshold, Type 1a supernovae tend to produce explosions of similar intrinsic brightness, making them useful standard candles after corrections for certain observed properties of the light curve. Within the local group and nearby galaxy groups, Type 1a supernovae provide distance measurements that complement those from Cepheids and help tie the distance scale together. Beyond standard candles, there are other techniques for measuring distances to specific types of objects. The tip of the red giant branch method uses the fact that red giant stars reach a well-defined maximum luminosity at a specific stage of their evolution, providing a standard candle applicable to old stellar populations. Planetary nebulae, the glowing shells of gas expelled by dying stars, have a characteristic luminosity distribution that can be used statistically to estimate distances to their host galaxies. Water masers, natural microwave lasers produced by water molecules in certain gas clouds, can sometimes be used to measure geometric distances through careful monitoring of their proper motions across the sky. Each of these methods has its strengths and its limitations. Each carries its own sources of uncertainty and its own range of validity. The art of measuring cosmic distances lies in combining them carefully, using each technique where it works best, and calibrating the connections between them as precisely as possible. When the different rungs of the distance ladder are well connected, the result is a consistent and mutually reinforcing picture of galactic and extragalactic distances that astronomers can rely on. The numbers we have been using throughout this exploration: 26,000 light-years to the Galactic Center, 100,000 light-years across the disk, 2.5 million light-years to Andromeda, are not arbitrary or speculative. They are the products of a long chain of measurement, each link carefully forged by generations of astronomers working at the limits of what their instruments could achieve. Understanding the chain does not diminish the numbers. It makes them more meaningful, because it reveals the human effort and ingenuity that went into establishing them. Chapter 11. The Milky Way in Numbers. We have spent the previous chapters building up a qualitative picture of the Milky Way, its disk and its arms, its center and its halo, its satellites and its place within the local group, and the methods by which we have come to know all of this. Now it is worth pausing to gather the numbers together in one place, not as a list to be memorized, but as a collection of quantities to be considered slowly, one at a time, allowing each one to settle before moving to the next. Numbers at this scale do not communicate meaning instantly. They require a little time and a little patience before they begin to feel real. The diameter of the visible stellar disk is approximately 100,000 light-years. This is the figure most commonly given, and it remains a reasonable central estimate, though as we discussed earlier, the outer disk does not end sharply, and measurements of its true extent vary depending on method and definition. Some surveys find stellar populations suggesting a disk diameter of up to 160,000 light-years, and the disk itself is warped in the outer regions, meaning the question of where it ends is partly a question of how you define the edge. For the purposes of developing a clear mental picture, 100,000 light-years is the working figure. 1 light-year is approximately 9.5 trillion kilometers. Multiply that by 100,000 and the result is 950 quadrillion kilometers, or roughly 9.5 times 10 to the power of 17 kilometers. These are numbers that have no natural human reference point. They exceed anything in everyday experience by so many orders of magnitude that the only honest response is to acknowledge that they do not fit inside ordinary intuition. What we can do instead is use comparisons that preserve the proportional relationships, even if they do not make the absolute scale feel familiar. If the Milky Way's disk were scaled down so that its full 100,000 light-year diameter fit within a circle the size of the continental United States, roughly 5,000 kilometers across, then our solar system would be represented by an object about the size of a single atom. The distance from our Sun to its nearest stellar neighbor, Proxima Centauri, would be less than the width of a human hair. At this scale, the entire volume of space that human spacecraft have explored would be invisible to the naked eye, a region smaller than any object you could hold in your hand. The thickness of the thin disk, roughly 1,000 light-years, scales in that same comparison to about 50 kilometers, roughly the height of the layer of Earth's atmosphere. The disk is, in this sense, extraordinarily flat relative to its width. If you built a physical scale model of the Milky Way's disk, using a sheet of paper to represent the thickness, that paper would need to be roughly 5 meters across to correctly represent the disk's proportions. It would be an extremely flat, extremely wide sheet. The distance from our solar system to the Galactic Center is approximately 26,000 light-years, just over 1/4 of the disk's full diameter. In the scaled model where the disk fits within the continental United States, this distance would correspond to roughly 1,300 kilometers, somewhat less than the distance from New York to Miami. We are not at the center of the disk, but we are not at the outer edge either. We sit in the middle regions, at a distance from the center that places us in a reasonably well-populated part of the disk, without being close to the more intense conditions of the central region. The number of stars in the Milky Way is estimated at somewhere between 100 billion and 400 billion, with 200 to 300 billion being a commonly cited range. The uncertainty in this number is larger than it might seem from the confident way it is sometimes stated. Counting stars in a galaxy you cannot photograph from outside requires indirect methods. Measuring the total luminosity of the galaxy, estimating the average luminosity per star based on knowledge of stellar populations, and dividing one by the other. Different assumptions about the distribution of stellar masses and the contribution of faint, hard-to-detect stars produce significantly different total counts. 300 billion is a number worth sitting with for a moment. If you counted 1 star per second without stopping, it would take approximately 9,500 years to reach 300 billion. If every person alive on Earth today counted stars simultaneously at 1 per second, the task would still take roughly 40 years to complete. The Milky Way contains more stars than any human civilization has lived through in years of recorded history, and each of those stars is a sun, a physical object of comparable scale and complexity to the one that warms our own planet. The total mass of the Milky Way in its visible components, stars, gas, and dust, is approximately 60 to 70 billion solar masses. The mass of the entire system, including the dark matter halo, is considerably larger, estimated at somewhere between 500 billion and 1.5 trillion solar masses, depending on the measurement method and the assumed extent of the halo. The visible matter, impressive as it seems, represents perhaps 5 to 10% of the total mass of the system. The rest is dark matter, distributed through the halo in quantities that dwarf everything we can see. The age of the Milky Way is estimated at approximately 13 to 13.5 billion years. The universe itself is thought to be approximately 13.8 billion years old, which means our galaxy formed very early in cosmic history, within the first few 100 million years after the Big Bang. The oldest stars in the Milky Way's halo are nearly as old as the universe itself, their compositions reflecting the conditions of the very early cosmos before successive generations of stars had enriched the interstellar medium with heavy elements. The disk formed somewhat later than the halo, with the thin disk assembling over a period of several billion years as gas settled into the rotating plane that we now inhabit. The orbital speed of the Sun around the Galactic Center is approximately 230 kilometers per second. The orbital period, sometimes called the galactic year or cosmic year, is approximately 225 to 250 million years. The solar system is estimated to be about 4.5 billion years old, which means it has completed approximately 18 to 20 orbits of the galaxy since it formed. During those orbits, it has passed through many different environments, different regions of the disk, different positions relative to the spiral arms, different distances above and below the midplane, each of which may have left some trace in the geological and biological record of Earth. The rotational velocity of the disk remains roughly constant with distance from the center, at around 200 to 220 kilometers per second across most of the disk's extent. This flat rotation curve, as discussed in the chapter on dark matter, is the primary evidence for the presence of a dark matter halo extending well beyond the visible disk. Without the dark matter, orbital speeds would decline with increasing distance, in the same way that planetary orbital speeds decline with distance from the Sun. The luminosity of the Milky Way, the total amount of light it emits across all wavelengths, is approximately 20 billion times the luminosity of the Sun. This sounds large, but it is a modest figure by the standards of galaxies. The Andromeda Galaxy is somewhat more luminous, and large elliptical galaxies can be hundreds of times more luminous still. The Milky Way is a fairly typical spiral galaxy in terms of its luminosity, neither exceptionally bright nor unusually faint for its class. The rate of star formation in the Milky Way is currently estimated at roughly 1 to 3 solar masses of new stars per year. This is a relatively low rate compared to some actively star-forming galaxies, consistent with the Milky Way being a mature galaxy that has already converted much of its available gas into stars over its long history. The star formation that does occur is concentrated in the spiral arms, particularly in the molecular clouds of the thin disk, where gas density is high enough for gravitational collapse to proceed. Taken together, these numbers paint a picture of a galaxy that is large by human standards, but unremarkable by cosmic ones. It is one of perhaps 2 trillion galaxies in the observable universe, a middle-sized spiral in a modest group, at an ordinary position within a larger supercluster. Its numbers are what they are, not chosen for any special significance, not arranged to place us at the center of anything, simply the outcome of physical processes that have been running since the earliest moments of cosmic history. There is a quiet honesty to that, and perhaps a certain comfort in it as well. Chapter 12. How the Milky Way Compares. Having spent several chapters exploring the Milky Way from the inside out, tracing its disk and halo and satellite system, and assembling its dimensions into a coherent picture, it is worth stepping back and asking how our galaxy fits into the broader population of galaxies in the universe. Is the Milky Way large or small, typical or unusual? Understanding where it sits within the range of galactic sizes and types adds another layer of perspective to everything we have considered so far. Galaxies come in an enormous variety of sizes, shapes, and masses. At one extreme are the giant elliptical galaxies, vast spheroidal systems containing trillions of stars, with little gas or dust and almost no ongoing star formation. These are the largest galaxies known, and some of them are extraordinary in their dimensions. The galaxy IC 1101, located about 1 billion light-years from Earth, is one of the largest known galaxies in the observable universe, with a diameter estimated at roughly 5 to 6 million light-years, 50 to 60 times wider than the Milky Way's disk. Its total mass is estimated at perhaps 100 trillion solar masses, compared to the Milky Way's total of roughly 1 trillion. It is not a spiral galaxy, but a giant elliptical, the product of many mergers over cosmic history, a vast and slowly fading system that no longer forms new stars in significant numbers. At the other extreme are dwarf galaxies, small and faint systems containing anywhere from a few million to a few billion stars. The dwarf, spheroidal galaxies that surround the Milky Way as satellites represent the lower end of the galactic mass spectrum. Some of the smallest confirmed galaxies contain only a few thousand stars, barely distinguishable from large globular clusters, except for their dark matter content and their more extended spatial distribution. These tiny systems are the most numerous type of galaxy in the universe, vastly outnumbering the large spirals and ellipticals that tend to dominate our mental picture of what a galaxy looks like. Between these extremes lies a continuous distribution of galactic sizes and masses, with the Milky Way sitting somewhere in the upper middle of that distribution. Among spiral galaxies specifically, the Milky Way is on the larger end. It is more massive and more luminous than the majority of spiral galaxies that have been catalogued, though it falls well short of the largest spirals known. The galaxy NGC 6872 in the constellation Pavo, for example, spans roughly 500,000 light-years across its disk, 5 times wider than the Milky Way, making it one of the largest barred spiral galaxies known. Our galaxy is large, but not extraordinarily so within the category of spiral galaxies. The Andromeda Galaxy, our nearest large neighbor, provides the most natural comparison. As noted in the chapter on the local group, Andromeda's disk is somewhat larger than the Milky Way's, spanning perhaps 200,000 light-years compared to our 100,000. Its total stellar mass is somewhat uncertain and has been revised several times, with some estimates placing it above the Milky Way and others comparable to it. What seems clear from more recent analyses is that the two galaxies are more similar in total mass than earlier estimates suggested, with the Milky Way possibly the slightly more massive system when the full dark matter halos are included. They are, in the broad sense, peers, two large spirals of roughly comparable size and mass, the dominant members of a modest galaxy group, slowly drawing together over billions of years. The Triangulum Galaxy, the third spiral in the local group, is considerably smaller than either the Milky Way or Andromeda. With a disk diameter of roughly 60,000 light-years and a stellar mass of perhaps 40 billion solar masses, it represents a more typical example of a smaller spiral galaxy. Many of the spiral galaxies in the nearby universe are of this scale or smaller. Modest, loosely wound systems with ongoing star formation, but nothing like the structural complexity or the sheer mass of the larger spirals. Looking beyond the local group, large galaxy clusters contain members spanning the full range of galactic sizes. The Virgo cluster, the nearest large galaxy cluster to the local group, contains around 1,300 confirmed member galaxies within a volume roughly 8 million light-years across. Among its members are giant elliptical galaxies like Messier 87, a massive system with a stellar mass of perhaps 6 trillion solar masses and a diameter of several 100,000 light-years, at the center of which sits one of the most massive black holes known, the very black hole that was imaged by the Event Horizon Telescope in 2019. Compared to Messier 87, the Milky Way is a modest structure. Compared to the dwarf satellites that orbit within the Virgo cluster, it is a giant. The comparison extends to other properties beyond size. The Milky Way's current star formation rate of roughly 1 to 3 solar masses per year is fairly modest by the standards of actively star-forming galaxies. Some galaxies, called starburst galaxies, are forming stars at rates of tens to hundreds of solar masses per year, their interstellar gas being converted into stars at a furious pace, triggered by gravitational interactions or mergers with other galaxies. The Milky Way has likely gone through periods of elevated star formation in its past, but its current state is that of a mature, relatively settled spiral, whose most energetic early phases are long behind it. The Milky Way's bar structure places it in the category of barred spiral galaxies, which account for roughly 2/3 of all observed spiral galaxies in the nearby universe. An unbarred spiral, with arms emerging directly from a rounded central bulge rather than from the ends of a bar, is actually less common than the barred variety, though both types are well represented in galaxy catalogues. The bar in our galaxy is a feature we share with the majority of spiral galaxies, a structure that appears to arise naturally in rotating disk systems through gravitational instabilities, and that plays a role in channeling gas toward the Galactic Center. Our galaxy's halo of globular clusters, containing somewhere between 150 and 200 confirmed members, is typical for a large spiral. Some giant elliptical galaxies host thousands of globular clusters, their large populations reflecting histories of many mergers and accretions. The Milky Way's more modest globular cluster population is consistent with a galaxy that has grown primarily through relatively gentle accretion of smaller systems, rather than through major mergers with other large galaxies. The overall picture that emerges from these comparisons is of a galaxy that is typical in many of its properties, not the largest, not the smallest, not the most active, not the most quiescent. The Milky Way is a fairly representative large spiral galaxy, one of countless similar systems distributed throughout the observable universe. It is large enough to have developed the full range of structural complexity we have been exploring, with a disk and a bar and spiral arms and a halo and a satellite system and a central black hole. But it is not so extreme in any of its properties as to be unusual or anomalous. This typicality has a philosophical dimension worth considering. If the Milky Way is representative of large spiral galaxies in general, then everything we have learned about it, its dimensions, its structure, its history, its relationship to dark matter, applies in broad outline to hundreds of billions of similar galaxies distributed through the observable universe. Our galaxy is not a unique specimen, but a sample of a common type, and understanding it deeply means understanding something general about the nature of galaxies as a class of objects. There is also something quietly grounding about the comparison. The universe contains galaxies that dwarf the Milky Way in every measurable dimension, and it contains galaxies so small that our entire galaxy would swallow them without noticing. We sit in the middle of that range, in a structure that is large enough to be rich and complex and old, but not so large as to be in a different category from the majority of galaxies in the universe. The Milky Way is, in the most literal sense, a typical home for a typical star in a typical part of the cosmos. And from that thoroughly typical vantage point, we have managed to piece together a picture of the universe that extends across billions of light years in every direction. That, perhaps, is the most remarkable thing about our position. Chapter 13. What its size means for life. We have spent most of this exploration focused on the physical dimensions of the Milky Way, its structure, its components, its measurements, and its place among other galaxies. But there is another way to think about the galaxy's size, one that connects its cosmic dimensions to something closer and more personal. The size and structure of the Milky Way are not merely astronomical facts. They have direct consequences for the conditions that exist within the galaxy, for where habitable environments are likely to be found, and for the broader question of whether life of any kind might exist elsewhere within this vast structure. The first and most obvious connection between galactic size and life is the sheer number of opportunities. A galaxy containing 2 to 300 billion stars contains 2 to 300 billion potential host stars for planetary systems. We now know from observations made over the past 3 decades that planets are not rare. The Kepler Space Telescope and its successors have established that planetary systems are the norm rather than the exception, with most stars hosting at least one planet and many hosting several. If even a small fraction of those planetary systems contain worlds with conditions suitable for life, the absolute number of such worlds in the Milky Way alone could be very large. But the relationship between galactic size and the potential for life goes deeper than simply counting opportunities. The structure and the history of the galaxy have shaped the conditions available for life in ways that are not immediately obvious. One of the most important of these is the distribution of heavy elements. The elements heavier than hydrogen and helium that are essential for building rocky planets and for the chemistry of life as we know it. These elements are produced inside stars through nuclear fusion and distributed into the interstellar medium when stars die, either through stellar winds in the case of lower mass stars, or through supernova explosions in the case of massive ones. Over time, successive generations of stars have enriched the interstellar gas with progressively higher concentrations of these heavy elements. This enrichment is not uniform across the galaxy. It is highest near the Galactic Center, where stellar density has been greatest and star formation most intense over the galaxy's history, and it decreases gradually toward the outer regions of the disk. The outer galaxy, beyond a certain radius, is relatively metal poor, meaning it contains lower concentrations of elements heavier than hydrogen and helium. Rocky planets can still form in metal-poor environments, but they tend to be smaller and less chemically complex. The conditions for life as we understand it may therefore be more favorable in the middle regions of the disk, where heavy element abundances are reasonably high, than in the very outermost reaches of the galaxy. The Galactic Center, despite its high heavy element content, presents a different set of challenges. The intense radiation environment near the center, produced by the high density of stars, supernova remnants, and the activity associated with the central black hole, would expose any planetary surfaces to radiation levels far higher than those experienced in our part of the disk. High-energy radiation can damage the complex molecules needed for biological processes and can erode planetary atmospheres over time. Whether life could survive or develop in such conditions is uncertain, but the environment is considerably more hostile than the relatively quiet outer disk regions. The concept that has emerged from thinking about these competing factors is sometimes called the galactic habitable zone. By analogy with the habitable zone around an individual star, the range of orbital distances at which liquid water might exist on a planetary surface. The galactic habitable zone refers to a range of distances from the galactic center within which conditions might be most favorable for life. The inner boundary is set roughly by the increasing radiation and gravitational disturbance of the central regions. The outer boundary is set roughly by the decreasing abundance of heavy elements in the outer disk. Between these two limits, a broad annular region of the disk may represent the most favorable environment for the development of complex planetary chemistry and potentially life. Our solar system sits comfortably within this proposed galactic habitable zone, at a distance from the galactic center that places it in a region of moderate heavy element abundance and relatively low radiation intensity. This is not coincidental in any deep sense. It reflects the physical conditions that prevailed at our galactic location when the solar system formed, conditions that were favorable for the assembly of a rocky inner planet, with the chemical complexity needed to support the processes that led eventually to life. But it does suggest that our location in the galaxy is not merely arbitrary. It is a location where the large-scale structure of the galaxy has provided conditions broadly suitable for what followed. The spiral arm environment also has relevance for habitability. As discussed in earlier chapters, our solar system moves in and out of spiral arms over the course of its orbit around the galaxy. The spiral arms are regions of elevated star formation, which means they contain higher densities of massive short-lived stars that end their lives as supernovae. A nearby supernova, within perhaps 30 light years, could deliver a dose of radiation sufficient to damage the ozone layer of a planet and expose its surface to elevated ultraviolet radiation for an extended period. Some researchers have proposed that major extinction events in Earth's history may be connected to episodes of elevated supernova activity in our galactic neighborhood, though establishing firm causal links across such timescales is difficult. The periods when our solar system was between spiral arms, as it is now, may therefore represent relatively quiescent intervals in terms of the local stellar environment. There are fewer massive stars nearby, fewer supernovae, and a somewhat lower flux of cosmic rays. This does not make the interarm environment safe in any absolute sense. The universe is not designed with safety in mind, but it does represent a less intense environment than the arms themselves, one in which a planetary surface is exposed to somewhat lower levels of energetic radiation over long periods. The age of the galaxy also matters for life. The Milky Way is approximately 13 billion years old, and the heavy element content of the interstellar medium has been building up throughout that time. Earlier in the galaxy's history, the available heavy elements were less abundant, and the conditions for forming rocky planets of the type that support complex chemistry were less favorable. Life of any kind that relies on complex carbon chemistry and rocky planetary surfaces may only have become possible within the galaxy over the past several billion years, as heavy element abundances rose to levels sufficient for the relevant planetary and chemical processes to operate. This means that the very old stars of the Galactic Halo, formed in the earliest phases of the galaxy's history, when heavy element abundances were very low, are unlikely hosts for life-bearing planets of the type we know. The disk stars, formed from progressively enriched interstellar gas over the past several billion years, represent a more favorable environment. Our Sun, at 4.5 billion years old, formed at a time when the interstellar medium had already been enriched by many generations of prior stellar evolution, providing the raw materials for a rocky inner solar system with the chemical diversity needed to support the processes that eventually produce life. None of this tells us that life exists elsewhere in the Milky Way. It tells us only that the conditions for life, or at least for the kind of chemistry and planetary environments associated with life on Earth, are not uniformly distributed through the galaxy, and that some regions are more favorable than others. The galactic habitable zone is a statistical concept, not a guarantee. A planet in the most favorable region of the disk might still be lifeless, and life might conceivably arise in far less favorable environments through pathways we do not yet understand. What the size and structure of the Milky Way do provide is an enormous number of possibilities, spread across a vast range of environments, over a timescale of billions of years. The galaxy has been running its experiment, stars forming, planets condensing, chemistry evolving, on a scale and for a duration that is difficult to fully appreciate. In a structure containing hundreds of billions of stars distributed across 100,000 light-years of disk, over 13 billion years of history, the conditions for life as we know it have existed in many places and for very long periods. Whether those conditions have been acted upon and what has resulted remains one of the most open and compelling questions in all of science. Chapter 14. The Galaxy We Cannot Photograph. There is a peculiar irony at the heart of our study of the Milky Way. We live inside one of the most studied objects in astronomy, and yet we have never seen it. Not truly. Every image you have ever encountered labeled as a photograph of the Milky Way is either an image of another galaxy, an artist's impression based on accumulated data, or a wide-angle photograph of the night sky, showing the band of galactic light as seen from Earth's surface. None of these is a photograph of our galaxy as it actually appears from the outside. No such photograph exists, and none can exist with any technology available to us today or foreseeable in the near future. The reason is simple and has been implicit in everything we have discussed. Our solar system is embedded within the disk of the Milky Way, roughly 26,000 light-years from the center. To photograph the galaxy from outside, we would need to send a camera to a position well above or below the disk, far enough away to capture the full structure in a single frame. The nearest point that would offer a useful external perspective would be perhaps 100,000 light-years above the galactic plane, a distance so vast that even traveling at the speed of light, which is physically impossible for any material object, would require 100,000 years of travel. At any speed achievable by current or foreseeable spacecraft, the journey would take billions of years, longer than the remaining lifespan of the Sun. The Voyager spacecraft, the most distant human-made objects ever launched, are currently at distances of roughly 20 to 23 billion kilometers from the Sun. That sounds impressive until you consider that 1 light-year is approximately 9.5 trillion kilometers. The Voyager probes, after nearly 50 years of travel, have covered a distance of roughly 1/1500th of a single light-year. The distance needed to photograph the Milky Way from outside is 100,000 light-years. The gap between where we have reached and where we would need to go is almost incomprehensible in its magnitude. This fundamental limitation shapes everything about how we study our own galaxy. Every piece of structural information we have about the Milky Way, the number and arrangement of its spiral arms, the length and orientation of its central bar, the full extent of its disk and halo, has been assembled from the inside through indirect methods by interpreting what we observe in different directions across the sky. It is a remarkable scientific achievement, but it is also an inherently constrained one. We are mapping a room we cannot leave, using tools that can measure certain properties of our surroundings, but cannot provide the direct external view that would resolve many remaining uncertainties at a stroke. The best external analogues we have for the Milky Way are other spiral galaxies at various distances. By studying galaxies that are similar to ours in mass, size, star formation rate, and morphological type, astronomers can build up a picture of what the Milky Way likely looks like from outside. The galaxy most often cited as a close analogue is NGC 6744, a barred spiral galaxy in the constellation Pavo, roughly 25 million light-years away. It has a similar size, a similar bar structure, similar spiral arm morphology, and a similar complement of satellite galaxies. Looking at NGC 6744 through a telescope gives something like a view of what an external observer would see when looking at the Milky Way, though the analogy is imperfect and the details differ in ways that are difficult to fully characterize without that impossible external photograph. Other commonly cited analogues include NGC 1232, a face-on spiral with prominent arms and a bar, and several other galaxies in the southern sky that share key properties with the Milky Way. None of them is the Milky Way. Each differs in some respects: different arm pitch angles, different bar lengths, different bulge sizes, different satellite configurations. The exercise of finding analogues is useful for building intuition about our galaxy's appearance, but it is ultimately an exercise in approximation. We are looking at cousins, not at the thing itself. The images that circulate online and in popular science publications as representations of the Milky Way reflect this fundamental constraint in different ways. Some are photographs of other spiral galaxies presented as illustrations of what our galaxy might look like. Some are composites, combining real photographic data of the Milky Way's central regions with artistic reconstructions of the spiral structure based on the best available models. Some are purely computational, generated from models of the galaxy's structure and rendered as images that represent our best current estimate of its appearance from a hypothetical external vantage point. These images are not wrong in any harmful sense. They communicate something true about the galaxy: its broad spiral structure, its bright central bar, its disk and halo, its satellite companions. But they carry an implicit caveat that is easy to forget. They are interpretations, not observations. The precise arrangement of the spiral arms shown in a popular science illustration of the Milky Way is a model, and like all models, it contains uncertainties and assumptions that the image itself does not convey. The actual appearance of our galaxy from outside may differ from these representations in ways that we will not know until measurements of galactic structure improve further. What we do have, and what is genuinely photographic rather than modeled, is a rich collection of images showing specific regions of the Milky Way in extraordinary detail. The central regions, captured in infrared and radio wavelengths that penetrate the obscuring dust, reveal the dense star clusters, the molecular gas clouds, the supermassive black hole and its surrounding structures. The spiral arms, traced through surveys of young stars and star-forming regions, are mapped in 3 dimensions with increasing precision. The halo, revealed through surveys of globular clusters and stellar streams, shows the archaeological record of the galaxy's past mergers and accretions. Each of these images is a real photograph of a real part of our galaxy, and together they provide a mosaic of direct observational evidence that no single external photograph could match in detail or in scientific content. There is also something to be said for the particular kind of knowledge that comes from being inside the structure rather than outside it. An external photograph would show the galaxy's large-scale appearance, but would not reveal the fine-grained three-dimensional structure, the detailed motions of individual stars, the chemical compositions of different stellar populations, or the subtle variations in stellar age and density that trace the galaxy's history. These are precisely the kinds of information that can only be obtained from inside, from instruments that can resolve individual stars and measure their properties directly. The Gaia mission's catalogue of nearly 2 billion stars with measured positions, distances, and velocities is a form of knowledge about the Milky Way that no external photograph could ever provide. In a sense, the inability to photograph our galaxy from outside has pushed galactic astronomy in directions that have produced a richer and more detailed understanding than a single image could have provided. The effort required to map the galaxy from within has demanded creativity and ingenuity, leading to the development of techniques and instruments that have advanced our understanding not just of the Milky Way, but of galaxies in general. The constraint has been productive, and yet the desire for that impossible external view persists, and it is understandable. There is something deeply human about wanting to see the whole of something at once, to hold it in a single glance and take in its full shape and scale. We can do this with other galaxies. We can photograph Andromeda in its entirety, trace its spiral arms, measure its dimensions, and hold the resulting image in our hands. We cannot do this with home. The Milky Way will not fit into any frame we can place it in, because we are always already inside it, looking outward at a universe that extends in every direction beyond the edges of the structure we inhabit. That limitation is, in its own way, a kind of intimacy. We do not observe the Milky Way from a safe and distant vantage point. We are woven into it, part of its stellar population, moving through it on a long, slow orbit that has been underway for 4.5 billion years. The galaxy is not something we look at. It is something we are inside of, and the knowledge we have of it has been assembled from that position, with all the constraints and all the richness that being inside rather than outside entails. Chapter 15. Reflections on Scale. We have come a long way through this exploration. We began with a problem, the difficulty of measuring something from within, and moved outward through the disk and its arms, through the Galactic Center and our own position within the structure, through the halo and its ancient stars, through the invisible architecture of dark matter, through the satellite galaxies and the local group, through the methods by which all of these dimensions were established, through the numbers themselves and what they mean, through comparisons with other galaxies, through the relationship between galactic structure and the conditions for life, and finally, through the peculiar intimacy of being unable to photograph the place we live. It is worth taking some time now, at the end of this long journey, simply to sit with what has been covered and allow the full shape of it to settle. Scale is difficult. This is not a personal failing or a limitation of imagination. It is a genuine feature of the kind of numbers we have been dealing with throughout this evening. The human mind evolved to navigate a world measured in meters and kilometers, to track distances relevant to finding food and shelter and other people, to remember journeys that could be completed in days or weeks. Nothing in that evolutionary history prepared us for distances measured in light years, for structures containing hundreds of billions of stars, for timescales of billions of years. The numbers we have been using exist at a level of magnitude so far removed from everyday experience that the honest response to them is not confident comprehension, but a kind of patient acknowledgement, a willingness to hold the numbers without fully grasping them, to sit in the presence of something larger than intuition can accommodate. And yet, something does get through. Not comprehension in the fullest sense, but a kind of orientation. After spending time with the structure of the Milky Way, after tracing its disk and its halo and its satellites and its position among other galaxies, the universe feels arranged differently than it did before. The night sky, if you have the opportunity to stand beneath it on a clear, dark night, looks different when you know that the band of pale light crossing it is the combined glow of hundreds of billions of stars, that you are looking sideways through a disk 100,000 light-years across, that the galaxy extends far above and below that band in a halo of ancient stars and invisible dark matter, that 2.5 million light-years away, an even larger spiral is slowly drawing closer. The sky does not change. The knowledge changes what the sky means. There is a particular quality to the scale of the Milky Way that distinguishes it from even larger cosmic structures. The galaxy is vast, but it is also, in some sense, local. It is our galaxy. Our sun is one of its stars. The atoms in our bodies were forged in earlier generations of its stars, scattered into the interstellar medium by stellar winds and supernova explosions, incorporated into the molecular cloud from which our solar system formed, assembled over billions of years into the physical structures that eventually gave rise to everything that has ever lived on Earth. The Milky Way is not merely a backdrop to our existence. It is, in a quite literal chemical sense, our origin. We are made of it. This connection between the large scale of the galaxy and the small scale of living things is one of the more quietly remarkable features of our situation. The carbon in every organic molecule, the oxygen in every breath, the iron at the center of every hemoglobin molecule in every red blood cell. All of it was produced in stellar interiors and distributed through the galaxy over billions of years before finding its way into the local molecular cloud, and then into the solar system, and then into the chemistry of Earth, and then into us. We are, in a genuine and non-metaphorical sense, assembled from galactic material, temporary configurations of atoms that have been part of the galaxy's ongoing chemical story for billions of years. The timescales involved in that story are worth dwelling on. The Milky Way is approximately 13 billion years old. The solar system formed about 4.5 billion years ago, meaning the galaxy had already been evolving for roughly 8.5 billion years before our sun ignited. During those 8.5 billion years, generations of stars formed and evolved and died, each generation enriching the interstellar medium with the heavy elements produced in their interiors. By the time the molecular cloud that would become our solar system began to collapse, the interstellar gas in our part of the galaxy had been processed through many stellar generations, acquiring the chemical complexity needed to build rocky planets with diverse mineralogy and rich organic chemistry. Life on Earth, in this context, is a late development in a very long story. It is a product of a galaxy that had already been running its stellar and chemical processes for the better part of its history before the conditions for life as we know it were assembled in this particular corner of the disk. The galaxy's age is not just a fact about a distant structure. It is part of the explanation for why we are here, in this form, at this time. The size of the galaxy also places certain permanent limits on what we can know and what we can reach. The distances involved are not merely large. They are, for all practical purposes, insurmountable. No technology we can currently imagine would allow a physical object to cross the Milky Way in any time frame relevant to human civilization, or to any civilization operating on biological timescales. The galaxy is our home in a comprehensive sense. not just where we happen to be, but where we are effectively confined, barring developments in physics that remain entirely speculative. The 100,000 light-years of the disk and the hundreds of thousands of light-years of the halo define the boundaries of a space that is simultaneously vast and, in the cosmic context, local. Within those boundaries, there are hundreds of billions of stars, most of them with planetary systems distributed across environments ranging from the intense radiation fields near the Galactic Center to the quiet outer disk where we reside. The galaxy has been running for 13 billion years, and the processes that produced life on Earth have been operating throughout that time in many different locations. Whether those processes have produced life elsewhere, and whether any of it has developed into forms complex enough to contemplate their own existence and their place in the galaxy, remains completely unknown. We have not heard from anyone else. The galaxy, as far as we can tell from our single inhabited world, may be very quiet, or it may be full of life that has simply not made itself known to us. Both possibilities are consistent with everything we currently know. There is something peaceful about that uncertainty, at least when approached from the right angle. We are here, on a small rocky world, orbiting an ordinary star, in a quiet corner of a large spiral galaxy, looking outward at a universe that extends far beyond anything we can reach or fully comprehend. We have assembled, through centuries of patient observation and careful reasoning, a picture of the structure we inhabit that would have been unimaginable to our ancestors. We know the diameter of the disk and the distance to the center and the mass of the dark matter halo and the age of the oldest stars and the identity of the black hole at the galaxy's heart. We know where we are broadly in a structure whose dimensions we can measure and whose history we can trace. And we know that this is enough, not in a resigned sense, but in a genuinely satisfying one. The Milky Way is more than large enough to spend a lifetime exploring in imagination and inquiry. Its structures and its history and its contents offer more to investigate than any civilization could exhaust. The fact that we cannot photograph it from outside, cannot cross it, cannot even fully map its outer reaches with current technology, none of that diminishes what we do know. It simply means there is always more to understand, always another question waiting at the edge of what has been established. The galaxy turns slowly. Our sun completes its orbit once every 225 to 250 million years, carrying with it all the planets and all the moons and all the things that have ever lived on any of them. In the time that one such orbit takes, mountains rise and erode and rise again on Earth. Continents drift to new positions. Entire branches of life evolve and vanish. The galaxy is indifferent to all of this, not in a cold or hostile sense, but simply because indifference is the nature of physical processes operating at scales so far removed from the human that the concept of concern does not apply. The galaxy simply is. It turns and forms stars and ages and moves through space, doing what physical systems of its kind do over the timescales relevant to physical systems of its kind. We are a brief and local event within that turning. 4.5 billion years of solar system history, a few billion years of life on Earth, a few 100,000 years of our particular species, a few thousand years of recorded knowledge, a few centuries of systematic science. Against the galaxy's 13 billion years and 100,000 light-year span, these durations and distances are almost immeasurably small. And yet, from this brief and local vantage point, we have managed to measure the galaxy. We have traced its arms and weighed its dark matter, and identified the black hole at its center, and mapped the orbits of its satellite galaxies. and established our own position within it with considerable precision. That, perhaps, is the most remarkable thing about the scale of the Milky Way. Not its size, which is simply what it is, but the fact that something as small and brief as a human civilization, on a small rocky planet orbiting an ordinary star in a quiet corner of the disk, has been able to understand it as well as we do. The galaxy is large, we are small, and yet the small thing has managed to comprehend, at least in outline, the large thing it finds itself inside. There is something in that worth sitting quietly with as the evening settles and the mind grows still.